Well, incidentally, we started with the sequences, and if you think about these are sequences. This is an example of a sequence that is has an application that is practical rather than theoretical. So we looked at limits of sequences, which is the main our interest from the point of view of theory, and later on we'll do it with series. But sequences, understanding sequences are very important because that's how we do any kind of simulations. Simulations, applications, anything that deals with data, anything that deals with computers. Computers don't do continuous computations. It cannot plot you a continuous curve. It cannot continuously compute your locations. That's how computers do things, and that's why sequences are especially important, apart from everything else. Okay, so like I said, this is the last topic for the test. So derivation of velocity from acceleration and location from velocity. So let's before we go back to the spreadsheet, let's review the underlying theory. So it is the theory is about approximation. So the question becomes approximations of derivatives and antiderivatives. Okay, so it's really uncomplicated but it does go way back to the very beginning of calculus 1, and that is where the derivative is defined. So f prime of a, that's the definition, is equal to the limit f of a plus h minus f of a over h. H goes to 0. Okay, so this is a theoretical point of view on the derivative. It gives you either instantaneous rate of change, it gives you the slope of the tangent line, it gives you the instantaneous velocity when f is the location. Okay, now once again, if we want to use computers, this is they do not take limits. So what do? We say that then this is the difference quotient. And this is the derivative. So the derivative is the limit of the difference quotient, and the derivative is approximated by the difference quotient. Okay, so in other words, replace f prime of a, f prime of x. So we're not really interested in one value at a time. So it's a function with another function, which is f of x plus h minus f of x over h. Okay, h is fixed, and it is our increment of x. Well, actually, let me put t there so we wouldn't be traveling too far. Okay, so replace the derivative with a difference quotient as its approximation. Okay, so as you can see, there is no limit, there is no differentiation, there is no techniques of integration, and half of what you learned in calculus 1 wouldn't be applied at all because it's algebra. So what's on the left is the algebra, and that's exactly how we do things. And then, but then, if we're interested in any kind of a simulation of physical processes, then there might be forces involved, and then what we're talking about then is the second derivative. So replace. So once f prime is found, so once this is done, then you might need more, and then what do? Replace f double prime of t with what? The same difference quotient, but of the derivative. So remember, the second derivative is the derivative of the derivative. So then if we know how to replace the derivative, we also know what to do with the second derivative. So we replace f double prime with f prime of x t plus h minus f prime of t over h. Okay? So that's the approximation. These little formulas over here, or both of them, are very easy to do with a computer or or a spreadsheet. We're going to do it at some point. We're not doing it because, for a simple reason, because we're going in the opposite direction. Remember, we're moving from the second derivative, acceleration, towards the first derivative, the velocity, and then back all the way back to f, the location. So if we reverse this analysis, then what do we have? So reverse. And then what we're talking about is antiderivatives. So I don't even want to write the integral sign, because we're not doing we are doing the integration. Riemann sounds implicitly, but it suffices just to look at these formulas in order to understand how we are moving backwards. So suppose f of double prime is now given, then f double prime is given, then we need to find f prime like this. So f double prime given by this formula, then what do we do to find f prime? We assume that we know the previous value, and we find the next value. So this is the formula. F prime of t is rather f prime of t plus h is equal to f prime of t plus h times f double prime of t. Okay, so that is the same formula. Well, this is what I'm looking at, is this. F double prime is approximated by this fraction over there. So if you just solve for f prime t plus h, okay, so this term, if I solve for this term over here, I will get this formula. It is an incremental formula, which means that you need to know f prime of t in order to get f prime of t plus h. So you start with 0 and progress one h at a time, getting more and more values of your derivative. Okay, but the formula is very straightforward, as you can see. So as long as you know f double prime, what do? You just keep plugging in, and you get a whole spreadsheet of values, which is what we did. And then we carry out the same plan for f. So f t plus h. So once done, we now getting the function itself following the same formula. So it will be f of t plus h times f prime of t. So once again, it is solving the. In other words, here we're solving this equation over here. F prime is equal to the difference quotient. So solving the equation for the difference quotient, which is supposed to approximate the derivative. We're going backwards, and we're getting the function from the derivative, and we do it twice if necessary. And we do that's why I do it twice, because I want to go back to the spreadsheet and do some more modeling. And these are the formulas that I use. These two, not the previous two. The previous two are sort of less interesting from the point of view of modeling, because they assume that you know location and then you find velocity and acceleration. This is not a typical situation, and certainly not what say Newton was doing. So the logic is the opposite. You know something about the situation, the setup. You know forces, or you know accelerations, and based on that you will figure out location. You want to figure out the trajectory, the path of that moving object. So that's why this is more important, this part. Okay. So once again, this is exactly what we did, except we do it twice. So this works for every function of t, and this is purely a mathematical thing. But you can have one function like this, you can have two functions like that. So here we have horizontal and vertical motion separately, and we do them separately. So this is, let me comment here, add some, okay, what is this? Okay. Okay, so this is time. This is the horizontal. This is then above is location, but we have one horizontal and three values. X double prime, that's acceleration, x prime is velocity, and this is location. And then I have the same vertical. Okay, three of them. So let me separate these so we can have more readable text here. Okay, so I separate x's from y's. I separate time from location. Okay, what else? I will put this underneath like this. And this one is a crucial part. This is the initial conditions. Okay, so the initial conditions here are where the location, initial location here, initial velocity. So these are the two horizontal location and velocity, and here two vertical and horizontal velocity, these two. Okay, so the problem that we solved last time was finding here. We were finding the we were trying to establish when, where, and how the ball hits the ground, and we just looked at this place over there where it is the location, the vertical location. That's that the column y changes from positive to negative. Okay, so from 9.6 it changes to negative 0.1. So that's where somewhere at that point it hits the ground. You then looking at the rest of the values here, the time 3.5 seconds since the horizontal velocity remains 200. Horizontal location is 700. So that's where things where it ended. That's how far it went. And the vertical velocity is 112, negative 112. So that's how far it's going. Okay, so you can ask different questions of the same kind. For example, you could ask a different question. For example, at what point was the vertical velocity, say, 50 feet per second? Okay, so you go to the table, to the column, this column, which is y prime, the vertical velocity, find where it is negative 50, right here, negative 50 going 50 feet per second, so you know that it will be after 1.6 seconds, and you know how far it went. At that point, it is 320 feet ahead. Another thing we can do, if I erase this, I could, no fail, okay. I could improve accuracy. So this, the answer was 3.5 seconds, which was close to what we did by hand. But we can do better. For example, we can improve accuracy. I could make my increment of time, which was 0.1. I could make it shorter, and that improves the accuracy we just talked about. So if I put here 0.05, as you can see, things start to develop slower, but with more accuracy of the approximation. So okay, so I don't have enough data. As you can see, this number is still this number. The vertical is still positive. So I need more time, maybe at least this much. Okay, so well, I have enough. So this is where the things happen. This is when it happens. So it's positive 1.2 feet above the ground, and then the next increment it becomes 4.48 below the ground. So that's where it happens. So the accuracy of my time 3.55 as well as the length 710 feet improved. Okay, so that is the data, and you can get a lot of stuff from the data, but certainly visualization is very important. So let's visualize this using what Excel has got. And you have to be very careful because we've got more stuff than in Calculus 1. We have three variables, t, x, and y. And graphs can be, then there are how many graphs? There are three graphs. Three variables can be paired up three ways. And so there will be three graphs. Okay, so it will be, let's start with the first one. So I'll go with t and x. Okay, t and x, how x, the horizontal location, depends on time. Fair enough. This is what we are interested in, or among other things. So I am simply plotting the just the, it is called the scatter plot. if you know Excel. So scatter plot, just click insert chart, and that's what we're seeing. So as you can see, those two, as I highlight over here my graph, the data is also highlighted. So you can see that the time and t and x are the two variables visible. Time t's are horizontal and x's are vertical here. Okay, so that should be it's important which way in what order they appear. Okay, so that's the starting point. As you can see, the development is linear. We knew that, so the horizontal progression is entirely at uniform speed. So every more increment of time, you acquire more and more, you move exactly the same amount, same length. Okay, so now the vertical is different. So I do the same. So I highlight t's and I highlight y's. Okay, so once again, insert scatter plot, the same scatter plot. Okay, so well, I have to fix it a little bit. Come on, like this. Okay. So well, that is the. Hold on. Where's my? Okay. So compare the two. So this is the graph now of y. So the one on the right is the dependence of x on y, x on t. This is the dependence of y on t. And as you can see, that's where we're getting something that is a parabola, even though the Excel does not know that is a parabola. It does not try to plot the parabola. It is doing nothing but plotting those pairs of points, so x's and y's. So you can see the purple highlighted on the left and the blue highlighted on the right. Okay, so the blue one, you can see, where's this one? Okay, so purple, t, and y is in blue, and that is with t horizontal and y vertical. Okay, so that's how you see what's happening on the. This is what a side observer will see. So somebody's watching the shot made, and from 200 feet above, as you can see, and as you can see, it is after this is time once again. Well, I'm sorry, that's not what's happening. Neither one of these are visible. Okay, so this is a dependence of location on time, and you cannot really see time not in the literal sense, but you can see that the discussion that we just had is still visible. So you can see that 200 initial altitude. There is no vertical component of the motion as well. We know that after 3.5 seconds it hits the ground, and on, all of these things we can still see. Okay, so that's all good. Now if we actually want to see the trajectory of the path through the sky of that object, you have to plot x and y. Not t and x, not t and y, as these are, but t and but x and y. So you got to eliminate the x. You got to eliminate t. So let me arrange these. Okay, so these are x and y as functions of t, but really interesting one is once again x and y. So, but fortunately it works out the exact same way. I have x and y, highlight them, and once again plot, create a chart, scatter plot. So I got to do this again. Okay, so the graph isn't that different. So this is what we're looking at is x versus y. Y. Okay. So that is the interesting one there. But so then you can see the difference between the graph that we have all the way on the right and this one. It is that the x-intercept is what is it, about 700. Right, so that is how far it goes. So x, it goes up to 700, and the vertical starts with 200 and then hits the ground at 700. Okay, so that's what we get from this. So once again, we're not plotting. We did not use any information from over here or from over here. So our analysis of our algebraic analysis right here is in fact. It has been ignored. So all of this analysis that we solve, all the problems that we cared, we solved them with algebra. Okay, so through integration. Okay, so we have that's how we got this formula. But we did not, once again, we did not take these formulas and plotted them. I plotted them through approximation. So through these algebraic approximations of our antiderivatives. Okay, so these two formulas are the only ones that I used. This one. So this is the spreadsheet. I used them twice. Okay, so why is it we're doing it numerically rather than algebraically? And the answer is we could easily tweak the results if we want to, including the situations when functions are impossible to integrate. But let's start to tweak this a little bit with, say, for example, what can I change? I could change the initial conditions. For example, I could assume that my initial elevation is 300. What's the change? No much change. The everything is automatically recomputed. I could make my initial velocity 100. And what changes now? Not much, so it goes at 100. I could also make a horizontal velocity, vertical velocity. I could add a vertical velocity to this situation. So in other words, I would put 100 here. So in other words, look at this column versus x prime. It means both of them are 100. So the horizontal velocity 100 feet per second, vertical velocity 100 feet per second. So it goes where I'm throwing at 45 degrees. Okay, I'm throwing at 45 degrees, and well, so not a lot. Everything else works out exactly the same way. I don't have to do any work, as you can see. So that is a clear parabola. You can see it starts, that picture on the left. It starts at 100 feet elevation, and it goes. You can even see that it goes at roughly 45 degrees up. And when it hits the ground, I will probably need more data in order to visualize that. Well. I wonder if I can do that. Okay, so let me make elevation lower. Now this one, initial elevation y prime. So how about 50? Okay, so well, it's still going so fast. Okay, 10. Okay, so it's still not reaching the ground fast enough for me to. Okay, there you go. So we start at 10 feet, and then at 10 feet, we start at the elevation 10 feet. We're throwing at 45 degrees. No, we're throwing at. We're really fast forward. Okay, so. It doesn't matter. Whatever numbers you enter them, the spreadsheet will work it out for you. So one thing we can try to do is once again to try to discover new things here. And one is what about that question that I asked last time, and that is this one. What if there is a horizontal? Yeah, right here. What if there is a horizontal component to gravitation? So an object is being pulled down because that's where the Earth is, but then there is a kind of part of the Earth also on the right. It's pulling at the same by the same force horizontally. Okay, so you could do it algebraically, but let's do it numerically because it is actually easier. So what do? How do I introduce a horizontal force? I change x double prime, that's right. So I just do what I have for y double prime, I do for x double prime. So instead of having here 0, over here rather 0, I'll put, how about once again negative 32? I'll put 32 because my positive direction in that way. So I'll put 32 here, so it will be exactly the same force pulling in the horizontal direction. So 32, and this is 32, so let me just spread it down. All the way down. Okay. I do not see a pronounced difference, even though, as you can see, this is where really things become as you can see, there is a certain horizontal. This is the graph that is just highlighted at the bottom. Is the, why is it? So let's take a look at these two graphs. This one has not changed. This is the relation of the vertical on time. We haven't made any changes to this part, so it works out exactly the same. This one is it is a parabola, but the parabola, why is it in the wrong direction? It coils this way. X prime 32. I said 32 in order for the pull to be from left to right. Let me make this number small. Yeah, okay, yeah, for some reason I thought, well, anyway, okay, so once again, these two graphs this is x versus y. It looks almost the same. It looks like a parabola, but is it a parabola? The one on the left. This is x versus y. Let's try it more symmetric. So how about I put x at, say, 50 and y at 50, and the velocity, both of them at 50. I'm trying to figure out, what is this with this thing? Just give me a minute. Okay. So is it a parabola? Is it a parabola? I think I might convince you that it is if I just try harder. Okay. So do you see a parabola yet? The picture on the left. You see a parabola? Well, I'm trying to drive to a certain goal. I do anticipate the answer. I just want you to. I want to show you that how you might try to discover things by numerical experimentation, pretty much. So what do I want? How about I put it? How about I throw it vertically? Yeah, how about I throw it vertically? Okay, does this help? Do you yet see a parabola? Well, that was overdone. Say 100. You see a parabola? Does it look like a parabola? Well, maybe not, but, well, here is maybe. How about I throw it backwards? I'll throw it backwards, say, over here, a y prime negative 10. So I'll be throwing, I'm standing on that hill and throwing this way. Okay, so I put negative 10 here. Well, maybe negative 50. Okay. So do you see a parabola now? Right. My point exactly. You tilt your head like this, and then you'll see a parabola. Do you see it? If you tilt your head to your left, then it totally looks like a parabola, which is okay. But what does it do? Does it Does it tell you anything? What's the meaning of that? So it looks like a parabola, but it is a tilted parabola. So there is acceleration in that direction, one acceleration, there is acceleration in that direction. So there are two forces. Okay, so what do we do with those two forces? So if we look at this picture, what we have discovered, it appears, we have discovered that the graph looks like this. Okay, it is a parabola, and what? Two forces. Can we combine them? So how do we combine them? Those two green arrows. One pulling down, one pulling to the right, but where is the really pulling is happening? What? Well, this is the parabola. The parabola is on this axis. The axis is skewed. Okay, so in other words, what it means is that the object is being pulled in this direction. So what does this picture mean to you? One force pulls this way, the other that way. What do you do with those two forces? Nope. It is a Pythagorean theorem, but it is more if you want to find what that value is, you do the Pythagorean theorem indeed. But the crucial part is the direction. The direction changes, and the direction, if there are two equal forces pulling in these two directions, the resulting direction of the force will get 45 degrees. Okay, so that's what you do with forces, or you do with acceleration. You do the velocities. You add them together and as vectors. So you've seen this in physics, maybe. If you haven't, you will see it in calculus 3 a lot of this kind of thing. So you will be dealing with vectors, and then indeed forces. Ultimately, there is only one force that goes all the way to Newton. So the acceleration is formed by all the forces taken together. And how do you add forces? When they're pulling in all different directions, possibly in three-dimensional space, you do vector operations on them. So in this particular case, you see those two green arrows, they added together, and they produce, according to this right triangle, it will go at diagonal. Okay, and then and that is what we're seeing here, 45 degrees sloped parabola. Okay, so it is actually the Earth that looks like this, like a corner. It will actually work exactly the same way as if the ground or the surface of the Earth were like this. Okay, it will be pulling it 45 degrees down. No, down, but 45 degrees diagonal. Okay, so like I said, the experimentation will reveal certain things. Experimentation with numbers, and especially visualizations, reveal things that are not obvious if you just do algebra. So that's the advantage of numerical studies. Visualization. Another one is what we cannot do, certainly not easily, is what if functions are more complex. Specifically, so we've chosen to, once again, we allow ourselves to travel in different worlds where, how about maybe the gravitational constant, or acceleration rather, this one, what if it is variable? What if it varies with time? So maybe it's like, maybe it's a comet. If it is a comet, then you know what comets do, they lose weight as they move through, so it is losing its weight. which means that your gravitation is getting smaller and smaller every moment of time. Okay, so if this is a function then like this, then what you end up with is then to solve the problem with the same variable acceleration, you would have to integrate right here. Okay, so that kind of integration may or may not be possible. We already seen a few examples, many examples. If you pick a random example, take a random example, it probably will be a function that you cannot integrate. Okay, so with all the possible, you have all the tables, all the computers available, but you cannot literally represent them the answer in terms of some familiar functions. So when it is a constant, it's easy. Anything beyond the function that we have seen, so some elementary sine, cosine, or some their combinations, we easily can run into trouble when we cannot integrate it. And if we cannot, what do we do? Well, the only way to do it is to integrate numerical. Ultimately, that's the only way to do to solve the problem. So that's what I want to do is to create exactly what I just said, and see what the trajectory is going to be when the gravity is decreasing in size, in magnitude. Okay, so I will eliminate this because, well, let me make a copy. So this one is gravity, and I will go back to regular Earth, flat, or not Earth. It's like I said, it's going to be a comet. So it will be 0. So there is no horizontal acceleration anymore. So we're going backwards in that respect. 0. Okay. What did I do? Nope. One more time. Okay. So that is my motion. I will put here, say 50 again. That is my throw. It is a parabola, just regular parabola, vertically oriented. What happens if now I'm going to change this from negative 32, and suppose either that comet is losing its weight, or, well, maybe Earth is falling apart or something like that. So any kind of function I can think of that declines, that will be decreasing in size. So negative 32, I'm gonna multiply by, so say starting with negative 32, and I will multiply by some function that approaching 0. So multiplied by what? Say. What function do you know that has a limit equal to 0? One over x. Well, let's divide by x, right? So x being t. Okay, so let's divide by x. Why not? Indeed, I'll divide by this number. Okay, so well, there we go. It might be declining too fast, then we'll see. Well, the point is that, well, 1 over x we can actually integrate, but it is, but you can see that it doesn't matter what formula I insert. Okay, so it starts at the large number and it ends with a very low number, as you can see. So that column is my acceleration. You can see how they're changing. So once again, the numbers are changing, and I don't see any difference in the pattern for some reason. So that is my throw. The result was, if I try to reproduce my data, so 200, the altitude is over here 200. Well, so do you see the result? So once again, look at the initial conditions. The horizontal velocity is 200, as initially we had. The initial altitude is also 200, which what we had. But look at the results. Look at the results. The declining gravitation. You see what the result of that? See here at the bottom on the picture. See how far it goes? Well, it goes farther, right? So I think the answer was 700 feet. it went when the gravity was constant at 32, and here it actually starts at, well, maybe starting at a little bit high value, but the point is that certainly this is not a parabola anymore, even though it is hard to argue because, well, I wonder. You can try to experiment, even though the picture seems to indicate that the trajectory flattens out. You know what happens? The parabola, it starts to go. You go actually deeper and deeper and deeper. That's what happens to the parabola. As you know, parabola, it has the derivative of a parabola is 2x. So if it goes down negative 2x, which means that it goes steeper and steeper down, and this one already appears to be flattening. So this one is not getting steeper. In fact, it starts steep and then less and less steep. So that is a kind of possible pattern you might see. So I suspect if you make gravity to decrease faster, it will indeed flatten out, which is predictable if you think about it. So what's going to happen if in the middle of the flight the gravity disappears? What's going to happen to the trajectory? It goes parabolically and then the gravity disappears. What happens? It will go straight line off the tangent to that curve if it disappears suddenly. If it disappears gradually as this, it will be kind of an oblique asymptote. So it will be approaching that straight line, as if at some point there is no gravity. Okay, so this is what the kind of things you can do with a spreadsheet and just this numerical integration. So take a look at the list of the problems there at the page, and the problems for the projects, so, well, not right now, but right after the test, and start working on what you want to pick, and as well as your partners. The numbers partners is to be developed, to be determined, because it's after the test. So, but I'd say 3 probably would be a reasonable number. Okay, so we will keep coming back to this when necessary. But really, it is a place where a lot of things come together. Numerical things, as well as integration differentiation twice, as well as several variables at the same time, rather than just 2. Okay, so that is the last thing is we're going to concentrate on next. So physics is out of the differentiation out, integration is out for a while at least, and we just look at these curves, curves on the plane that are not graphs. Okay, so let me make that clear what I'm talking about. So they're called parametric curves. So curves that aren't graphs of functions. This one, the example we just did, is an example of such a function. This one, okay. So this cannot be the graph of a function. Why not? That's right. So also known as the vertical line test. You draw a vertical line and it has 2 values for y for the same x. It's not a function. Okay. So vertical line test. This one passes, and this one does not. Well, say like this, fail. Okay. So vertical line test. Every vertical line has 1 intersection, and this one it has 2 possibly. Okay. So that's a fail. So 2 y's for 1 x. That's the failure. Okay, so but we're still interested in these curves. Why? Well, any kind of motion does not know on the xy plane. That is, remember that that we talked about graphs of x or a function of t, y function of t, but really if we're talking about paths or trajectories of motion, then they are on the xy plane, and there is no, well, it's not an xy plane. It is what it really is a plane, a piece of paper, and then there is a bug moving around. Okay, so which way does it move? We don't know. It can do it in any way it wants. It could not only come, make a loop and come back, but it can actually cross its own path eventually, like this. Okay, there is no restriction whatsoever in that respect. So before doing any kind of calculus with that, and there is plenty of it to do, because these curves that we're looking at right now are more general than the curves we saw in calculus 1. So to be clear, curves that are not necessarily graphs of functions. Okay, so we still include all the graphs of functions, but these are more general. So these are more general. There are more of them. And number one example is circles. Is this circle? So this circle is the number one example of parametric curves that you wanna to be able to handle. Okay, so we'll do it next time. So tomorrow, bring your questions so we can talk about the test for a while.